Hello everyone. Welcome to the third day of the New Year's seminar of the Chinese-German Chemical Association. My name is Chang Ding. I'm a group leader in the Department of Molecular Environmental Biotechnology at Helmholtz Center for Environmental Research. So today we have the honor to invite 4 speakers. So they are in the background of either biochemistry or environmental chemistry. So without delay, we come to the first speaker. So Dr. Cui Haiyang, who is a professor currently at the Nanjing Normal University in China. So he was also once a member of our association. So we really are happy to see him again, face to face. So Dr. Cui obtained his PhD degree from RWTH-Aachen University in Germany in 2020. And after that, he did his postdoc study at the Leibniz Institute for Interactive Material at DWI in Germany. And at 2021, he went to the US at UIUC for another postdoc. And before he then joined the Nanjing Normal University as a professor. So he has published more than 20 first author papers, including Science, Angewandte Chemie, and so on. And his work is focused on synthesizing. His work is on molecular simulation and machine learning with protein engineering, spearheading transformative advancement in biocatalysts. Without delay, then I give the stage to Professor Cui. You can already start with your presentation. Welcome.
Yeah, thanks, Ding's introduction. So it's my pleasure to to share my research work during in UIUC in America. Before my presentation, I also want to say Happy Spring Festival. Although it's just like 4 days before, yeah. So today I will share the work like when I did my postdoc in US. So the topic is enzyme function prediction using contrastive learning. So before that, sorry that I prepare a Chinese slide that's to introduce myself. But I will introduce this in English. As Chang just mentioned, so I started my bachelor in China and also my master in China, and then I went to RWTH-Aachen for my PhD, and then I did 2 postdoc in DWI and UIUC. So in this year, at the beginning of this year, I joined the Nanjing Normal University, so to be a professor. As he just mentioned, I published few research articles. So mainly focus on the computer-assisted enzyme engineering field. As we all know that biocatalysis is evolving in various fields. For example, in fine chemicals, also the food field, also the pharmaceutical fields. So biocatalysis is very important tool that for performing the reactions that's then achieving the target compounds. So recently that there is a trend in our biocatalysis field is that so the field try to integrate some novel technologies. So one of the top, I would say the top technologies, artificial intelligence is like the machine learning or deep learning, and also other enzymatic total synthesis like methods. So the left side shows the AI already involved in like different fields. For example, the protein design or the direct evolution fields, and also the genomics and metabolics fields. So for a successful biocatalysis, so the first step is that we should know the enzyme function or the protein function. So UniProt is a popular like database to UniProt is a popular database that's involving all these protein sequence. So until now, there are around 100 sequence in the database in the UniProt, but only like less than 3% they are reviewed by human curators. So like only this this percent that's like curated by the human, but in this only like only like 20% of them they are supported by the experiments. So we could see there is one example that's I shows like the two different like time points. One is April 2022 and also April 2023. We see the involved sequence is about 15 million, but the revealed one only like around 2K, like 2000. So which means most of the data or the protein sequence is still not revealed. Even they are revealed, but 40% of them they are incorrectly annotated. So this is like a common challenge for our protein science field. Usually that we will use BLAST is a computer tool to do the sequence alignment and then to annotate the protein function, but like around 33% of sequence still cannot be annotated automatically. Then for the using the machine learning technique, as we also have some machine learning tools to annotate the sequence, to annotate the function of the protein. But honestly, that's the most machine learning algorithm. They are less accurate than the BLAST, like than the traditional method, and also for the understudied functional functions, still lack of the data. So we know for machine learning methods, they really need a huge data. Otherwise, it cannot learn the truth of the data set. Generally, that's so here I propose a question like how does the traditional machine learning work for the classification task? So the protein function task can be as a classification task. So for the training data set, for example, here I use a simple cat and dog classifier as an example. Within the image of the dog or the cat, so the machine learning model can extract some features from the image, and then during the training we minimize the loss of our loss function. Then we can know like whether it's a cat or dog. So it's like a simple classifier. And then this is for the training process. And then for the predict, when you have an unknown image, then you input this unknown image to the trained model, and then the model can give you the results. But this is usually for machine learning training that's we should have a balanced data set. But if what if the data is extremely unbalanced? So why we need a balanced data set? You can imagine that, for example, if here we have 100 image of the towards the cats, but only one image for the dog, then the model can easily learn, like, okay, I just predict the cat, then I have like almost 99% accuracy, right? And so that's the a traditional challenge that's the traditional classifier or the traditional machine learning model will face. If the data is extremely unbalanced, then the model usually cannot work well. So here we propose that use contrastive learning. So the main difference is that we don't learn the label directly, but instead we learn the similarities. So here is that first we train, like here, we train the model to recognize the different like cat and dog. So if they are the same, then we will make the distance between the queried queried one and also the reference one much closer to each other. But if no, if they are different, then we like make the distance much longer between them. But if they are similar, like they are all belongs to cat, but with different images, then we should let the model learn that they should the distance between them should much closer. So then in the predict process, so if we have an unknown query, then we just compare the unknown query, the distance between the unknown query and also the dog reference. So here the dog reference will be like a golden reference. So it's average all the features of the dog. And then if the distance is much closer, then we know they are the same. If the distance is much longer, then we know they are different. So then with this contrast learning, then we can like figure out the imbalanced data. So come to our enzyme annotation task, enzyme function annotation task. So here we developed a tool called Clean. So in this case, here we use the EC number to stand for the enzyme function. So the EC number is include like 4 digits of the numbers. So in the training process, if they have the same EC number, so here is like the positive sequence and also the anchor sequence. Then if they have the same EC number, then we should minimize the distance between the positive and the anchor sequence. But if they are different, they have different EC numbers, then we should the model should learn that maximize the distance between the negative and anchor. Yeah. So yeah, as I just mentioned, they have like 4 digits. So after training, then we will know that for the query one, we will compare the distance between the query and also the golden reference. If they are much nearer to one EC number, then we will annotate this EC number to the unknown sequence. With this developed clean tool, that we also compare with the other like the state of the art annotation tools. So one is protein infer. So this tool is developed by Google. They published it in 2023, like just before our work, like 2 or 3 months before our work, but they only is published on the archive website. Bioarchive website. So, and also another one is called DPEC and EC Pride. So we say for the precision and recall and F1 score, that's our clean consistently outperformed this multiple baselines on the general data sets. So here the general data sets, one is the new 392 and another is the price 149. For the new 392 is that this is the newly released data after we train our model. So it's in total is about 390 sequence. And another one is the include 194 sequences. So they are all of them are misannotated sequence, and then they are they were experimentally determined and then annotate them. So we could say from all these three characterization that we all outperform them. And we know that the data size. The data site size is very important, and then as I just mentioned, the unbalanced data either 100 or 1 data in the data site. So we could say for the EC accuracy that our clean mode, our method is shows always very consistent performance against the biased data, but for the other machine learning tools, that they show a clear decreasing as number of training data decrease. After that, we perform the experimental validation, and here we choose a halogenesis data site, and this data site is in total that we reviewed around 400 papers, and then we found around 300 halogenesis which reported in the literature, and among those there were 36 incompleted annotated halogenesis that they already identified from the UniProt, and also this 36 incompleted annotated halogenesis, it covers all 4 types of halogenesis. Yeah. After validates on this collected in-house data sets, we found the clean achieves much better prediction accuracy. So the accuracy is from 86.7 to 100%, and compared to the 6 other commonly used computational tools. We test from the first digit to the 4th digit. So all those 36, most of them we can validate the results by the reported literature, but there are still 3 enzymes. They show some conflicting results, even in the literature report. And also we found our clean annotate different results, annotate different results compared to the other tools. Then those 3 enzymes, they are TTA0338 and MG1651. So also the SSFLA, this the name of the 3 enzymes. All those 3 enzymes, they belong to the SAM-dependent halogenesis. As I just mentioned, this is one of the 4 halogenesis family. So we don't know what's the function of them, but in the literature, that's some of the one literature, for example, for the MJ1651, so they report this enzyme is chlorinase, but after they solve the crystal structure of the protein and then they perform the reaction, but they can't find the chlorination reaction performance for this enzyme, then it's still like unknown. But for the SS FLA, so this is the fluorinase, so it's this enzyme can add the fluoride, this atom to the SAM part. Then we use the HPLC and also the tandem mass spec to validate our finding. So interestingly, that instead of the like halogenation reaction for the enzyme, we found actually the unknown in these two unknown enzymes, they are hydrolase. So it's as the OH group to the SAM instead of the halogen atom. And also we found for the SS FLA, this enzyme has like 3 functions. So here the mentions didn't mention that the light yellow is like here we label annotates with 1 is the substrates, and then the orange and the light green and the dark green, they are the substrate. They are the product. So we see for this enzyme, it's not only produce the 4, it's the the fluorination product. It also can produce the number 2 and also number 3 products. Which in the indicating this SS FLA is also like a chlorinase, and also another function is the hydrolase. So luckily that's our clean or answer, gets the correct answer, like did a great job for the prediction, and but for the rest only the blast P like gets 1 correct answer, is for the TTA0338. So another interesting finding is that actually our model is only based on the sequence embedding. So which means we didn't extract any structure level information from the protein, but we found here we superimpose those structures of the enzyme. Like we found this from the structure level, they are very similar to each other, but our model with only the sequencing with the sequencing information is already can distinguish the different function of them. This is which like a bit surprised us. So here I summarize. Okay. Yeah. So that's sorry for the unexpected sound. Yeah. So here I use the Chinese to summarize the main results of my work. So the first is that we use contrastive learning to annotate the protein functions, and the method we call is clean, and also it can annotate the unknown functions, and also can distinguish the promiscuous of the enzyme, and we correctly annotate the EC number to the enzyme, and also we test it on 36 unknown halogenases. And in the end, I want to acknowledge my supervisor in UIUC is Professor Huimin Zhao, and also my cooperator, especially Tian Hao, that's which we cooperate for this specific work. And also I want to thank for my undergraduates and also our lab manager and my friends in Zhao's lab. Thanks for your attention.
Okay, thank you very much. Yeah, thank you very much. Maybe you can still keep your sharing because we will have some minutes to ask questions. Maybe I can already ask some questions. So it's is it an open source tool? So I mean, can we already access to this tool if we want to annotate or assign the EC numbers to the enzymes that we are interested in?
Yeah, exactly. We have websites, and it's an open tool, and you can download it from the GitHub if you want to run it locally. And then we also have a website that you can directly input your sequence, and it will annotate the EC number for you.
Does it also?
Yeah, later I can share the link in the chat.
Yeah, that would be nice. Does it also provide like a score for prediction? So for example, 80% probability for this assignment, or you have to trust what it tells you?
Yeah, certain for like a confidence number for each prediction. And but in the website we don't show this score, but in the GitHub version you can get it. Yeah.
Okay, so it's possible, but you have to install it by yourself.
Yeah, exactly.
Are there other questions from the Zoom audience? I can also, because this is also at the same time broadcasted on an online platform, so maybe there are also some questions there. And for the Zoom audience, you can either unmute or write in the chat, which are both fine. If not, maybe I just have another overall question. So it seems that your model or your prediction for the EC number is so much more advanced than the other existing models. So it reminds me of AlphaFold, which came out to be so much better than all the other tools for protein structure prediction. Do you consider this also as also equally revolutionary as the AlphaFold? And do you still see there's still room for improvement, or would you say it's already pretty much the best result that we could get with the prediction?
I would say for the EC number, this is the current topic tool, like till now. So I would say because here we simplify the enzyme like enzyme function prediction. So we just predict the EC number. So I would say the most like the biggest achievement or for our work is that we introduce the contrastive learning to our to the field, and then is all the classification work. I would say the contrastive learning most likely can contribute its role there. Yeah, this is one big like contribution for our work.
Yeah, so it's a new algorithm, let's say.
Yeah, but this algorithm is already like used in other field, but in this field, this is the first time we use it. It performs very well. Yeah.
Okay. If there are no more, I can have another question, maybe. I mean, we still have a bit time. Can you go to page 13, where
13. Okay.
yeah, where you mentioned that this the prediction is really accurate, 87% to 100%.
Yeah.
But in your, I think 3 slides before, you also gave the score, which shows around 0.5, 0.6 is already the best for clean. What does this score mean? Isn't that also, does it also not mean accuracy? Why is this 0.6 and here is almost 100%? Maybe I didn't get it.
Yeah, the previous one, so they are like tests on different data site. So here, this percent is specifically for this halogeneity site, but the other scores is for the other tested data site. Yeah, that's why we have different like accuracy or often different scores.
Okay, so it has different accuracy or different performance, let's say, in for different categories of enzymes.
Kind of, yeah, for different test data site.
Okay,